The normal strategy that you want to apply for an outage is to have all of the work defined as much as a year in advance, to have all of the tooling and the spare parts assembled, all of your mock-ups ready to practice in, so that when you actually shut down, the work is done as efficiently as it can be done. Now, the situation here is different. It does occur in the industry. It's what's called a forced outage. In a forced outage, you're presented with a problem and you do not have time to prepare. So the challenge in a forced outage is to very quickly understand the nature of the issue that needs to be dealt with, and then how you're going to repair it, and to bring in all of the resources necessary in order to implement that as efficiently as possible. And that's what I see happening here. The challenge was getting the information because of the difficulty in accessing the area that we need to repair. And having said that, we now have all of that information, and in parallel with that, all of the repair tooling, the mock-ups to practice have been moving ahead, and it's all coming together now, and we will be applying that repair. We started with the fundamental premise of we need to go with technology that's proven. And we chose well buildup. And we chose that mainly because it gives us a broader range of repair, and because we were able to find a supplier who has some experience in this type of work. So the application of it can be done with a high degree of assurance that it's going to give us a good and lasting repair. The challenge is the location that we have to repair, because we're looking at doing all of the work from at least 30 feet away from the site. We need cameras to watch the welding process. We need to do non-destructive examination of the finished weld to assure that it is complete and there are no flaws and that we've added the amount of material that we intended to. So the challenge is the remote location, not the technology. The technology is proven. In nuclear, you can't afford trial and error. Things have to be right the first time. So it's attention to detail in planning every activity, in planning it down to the smallest level of task so that everyone understands exactly what has to be done. It's attention to detail in the design of tooling so that the tooling that we design is going to work right the first time, it's going to be reliable, it's not going to malfunction when you need it. So really that professionalism is around discipline. It's around creating and using procedures. It's around having processes that drive the planning down to the greatest level of detail so that when we actually execute, we're successful. And that's where practice and mock-ups come in, because we've built a replica of the reactor deck of the NRU, and we can use that to stage the teams with all of their equipment, and we practice. And we practice until we get it right. And then when we get it right, we practice some more, and then we bring it here and implement it. We've got the equivalent of about 300 people working on this project, and the work level of intensity is high. The timing is critical. We can't afford to miss a step. We can't afford to waste a minute. We have the right team on this job. You could not find a better group of professionals to be executing this repair on the NRU. AECL as an organization, our business is solving tough technical problems. And so when nuclear plants around the world face challenges, they come to AECL. We're applying that same expertise here for the repair and return to service of the NRU. We're also calling on outside experts. We've brought in experts in the examinations that we're doing, in understanding the corrosion that we need to repair, and in providing the repair technologies that we're going to apply. So we're using the best that we've got, and we're also using the best the world has to offer. And that's where you can have the confidence we're going to come in on schedule.